Okay, so we finished off last class and we just went through this one factor kind of what we call a randomized block design, where again we have these four different brands of golf ball, and the brand is the factor, and the factor levels are brand A, brand B, brand C, and brand D. And then we have the golfers 1 to 10, which is like the blocking variable. As I said in class, the idea is if you have variation within golfers, that variation is kind of removed from the error term in the randomized block design. And again, go back to last class's notes where I drew out all the sum of squares on the board and we discussed that in more detail. But anyway, let's just kind of repeat what we did in SPSS, and then we will actually do this as a hypothesis test. So we're going to do analyze, general linear model, univariate. Now, the dependent variable, of course, is the distance, and we have two factors, golf and brand. Now, this is just, we're just kind of considered to be two factors, but the main thing is we don't want, in this particular design, we don't want the interactions between the terms. So if we go to build terms, select golfer and brand, select main effects, and click OK. Select OK. Okay, let's also do some plots. So we can have one that plots the different brands. We'll have one that plots the particular golfers, although we're not particularly interested about the difference between the blocks. Going to my example last time, you know that Tiger Woods is a better golfer than me, but you know, in some experimental conditions, you may be interested in the blocks. So let's add this. But let's do some post hoc tests. And here we really are just interested in interested only in the brand. And to avoid any confusion, we're just going to do one, which is going to be the Bonferroni. So click OK. And let's just kind of have a look at our overall ANOVA. You see that everything is significant in the overall ANOVA. The brand, which is our factor, has an F value of 54.31, significant. The golfer, which is the blocking factor, is also significant. And therefore, both of our tests are going to be significant. So let's actually now kind of do this on the kind of the whiteboard and just do it as a formal hypothesis. Okay, so let's write this on the board. So our business hypothesis. This is basically, does the distance traveled differ across the four brands? When we're blocking by the golfer. So when blocking by golfer. And we're going to test it at alpha equals 0.05. So the scientific hypothesis now this is completely the same as the completely randomized design. Basically, all the means are equal. And the alternative hypothesis, the mean distances differ for at least 2 brands. Okay, let's move that up a little bit. And the test statistic is that F is the mean squared treatment all over the mean squared error. And then the rejection region. We've got alpha equals 0.05. Now, the degrees of freedom for this test are k minus 1. And that's the numerator degrees of freedom. Denominator degrees of freedom are n minus k minus b plus 1, where k is the number of factors and b is the number of blocks. And this comes from the ANOVA table that we went over last class. So we can see here, treatment mean for the treatments is k minus 1 degrees of freedom, blocks b minus 1. We kind of derived this and talked about this in terms of the sum of squares last class. And the error term is n minus k plus minus b plus 1, because everything needs to add up to n minus 1 degrees of freedom. And we need to subtract these values, which leads us to n minus k minus b plus 1. So let's kind of go back to our calculating degrees of freedom. So here we had 4 brands. So k equals 4. We had 10 golfers, so b equals 10. And our total number of observations, and the total is going to be 4 times 10 equals 40. So again, you can see this from, if you were to go back to SPSS, you would see that you would literally have the 40 observations here. Okay, so let's just go through this. Degrees of freedom, 4 minus 1. Whoops, I don't know what I did there. I think I made it a bit bigger. 4 minus 1 is 3. And 40 minus 4 minus 10 plus 1. Remember that I'm going to circle this because it's so easy to do minus 1. I've done that on the board and embarrassed myself before. That's going to be 40 minus 14 is 26 plus 1 is 27. And we're going to reject H0 if F is greater than F alpha with V1, V2 degrees of freedom. And since we're setting 0.05, this is going to be F 0.05, 3, 27. Okay, let's move that up a little bit. And we just so happen to have the F table here. Numerator 3, go down, 27 across. And you can see that we have 2.96 here. Let me just do a zip of that. So, what do we all really want? Green. 327. And we're left with 2.96. I'm going to keep that there for kind of the blocking factor. Let's actually get rid of the original. Okay, so that's going to be equal to 2.96. And we can make that a little bit smaller again. So like we can actually draw that. Sorry, that's not a very, it's more like a chi-squared distribution. It should be a little bit more peaked there, but I'm not an expert at drawing on these tablets. And we've got the kind of the F critical is 2.96. So calculate the test statistic. And again, I might give you an ANOVA table to fill in the gaps, but here we're just going to use SPSS. So F is going to be the mean squared treatment all over the mean squared error. So let's go back to SPSS. And so you see the treatment is the brand, and this is going to be the mean squared treatment is going to be 1099.552, and the mean squared error is 20.245. We divide those to get the F statistic. So I don't, if I ask this in a question, I generally ask you to do the ANOVA table. But even if I gave you the SPSS output, you'd kind of want to do this at a minimum. And then the conclusion is F is 54.31, which is greater than 2.96. So we can reject H0. Now, the one little thing that we want to do is, let's just say I ask you to calculate the blocking factor. So let's just put a line under this. So say this was an exam and I said 2, is the blocking factor significant? Now, we're not going to do a formal hypothesis here, but let's just see how we'd go about it. So again, we go back to the ANOVA table, and the blocks is B minus 1, and we have the mean squared block. And again, when I did this on the board, I added an extra line to show you how to do this. And it's going to be the mean squared block divided by the mean squared error. So, and let's just look at the degrees of freedom. So we have B minus 1 degrees of freedom for blocks, and N minus K minus B minus 1 plus 1 for the error. So let's just actually do the rejection region first. So here we've got alpha equals 0.05. We've got V1 equals B minus 1 equals 10 minus 1 equals 9. And it's the same error term. So we have N minus K minus B plus 1, which we know from before that was 27. This does not change. So that's going to be basically 10 minus 4 minus 10 plus 1. Sorry, 40 minus 4 minus 10 plus 1. So we're going to reject H0. And this would just be, we've not written it out, but this would be all the block means are equal. If F is greater than F 0.05, comma V1, 9, and 27. So let's go back to our little snippet here. So we can actually go across, numerator 9 and 27 is 2.25. So we can actually, now we can actually just check what was in SPSS. So in SPSS, we have the calculate test statistics. And this is just going to be F is going to be the mean squared block all over the mean squared error, which is going to be equal to, let's just get SPSS up. The golfer is a block, so it's going to be 1341.542. All over. The error doesn't change, so it's 20.245. Let's just see if I've remembered that correctly. Yeah, 20.245. And the result is, for the golfer, 66.265. I won't bother writing out a separate conclusion section. We're not doing this formally. Which is greater than 2.25. So we're going to reject H0. And there's evidence that the golfers are different, evidence of some difference in golfers. And final little thing, let's just look a little bit back at SPSS. And I won't go, because we did this last class, but if you just look at the post hoc tests, and let's just look at the marginal means, these really haven't changed. That you can see this time we've got D as the lowest, then we have A, then we have B, and then we have C. And obviously there's a whole host, there's no real kind of rhyme or reason for the difference between the golfers. It's just kind of general heterogeneity. And we can basically see at alpha equals 0.05, all these differences are significant. So we can see here that D is the lowest, and like A is the highest. So everything for D has, you know, a kind of a confidence interval where D minus the other brand is the confidence interval doesn't go through 0 and it's less than 0. So we have D at the bottom. Then we have kind of next up, we have A, and if we look at A, we can see that D is positive, but the 2A confidence bound, you know, the B and C are negative. So A minus B and A minus C are both negative. So again, B and C are greater. And then you can just see that B minus C is negative. So B is obviously less than C. So there is at alpha equals 0.05, there is a significant difference between all of these brands. And it would go DA. Let's just kind of look. DA, B, and then C. And unlike last week, when I kind of drew the line over the bottom two, because there wasn't a significant difference in between them, at alpha equals 0.05, there's a significant difference between all of the means. So we could actually write it out like this. Okay, and that's it for ANOVA with blocking factors.